record the video. Yeah. Okay. So previously we studied the dispersion, right? Dispersion. What is the dispersion? So I use the same chart, right? So let's do U ZT, right? So use 0t here. And first, we want to convert it to U 0 omega tilde, right? We do take the Fourier transform because the dispersion effect play on the frequency domain, right? Play on the frequency domain. So each of these components have different delay, right? So then we take a propagation, right? Remember what is the propagation is that U z omega tilde is U 0 omega tilde, right? Times exponential I over 2, right? K naught double prime omega square z, right? K naught double prime, right? K naught double prime. Of course, you can add the third order dispersion. You can add the third order dispersion. But what dispersion plays a role is that for each this frequency component, you add different time delay, right? This is called dispersion. This is called dispersion because when the when the light pulse propagating through the medium, right? Through the medium, it actually adds a dispersion because the medium responds differently for different wavelengths, right? This is called dispersion effect. Yeah. Okay. So we got this U Z omega, and then we come back have the U Z T, right? We take the inverse Fourier transform. So we have this different step, and effectively we propagate, right? Effectively we propagate. So I designed the. I know there's a lot of learning curve for the material, a lot of derivation. It's kind of very heavily involved a lot of series derivation. But I hope the lab session helps a lot in terms of understanding how to use MATLAB. All this would be very useful, I think, in the future, right? And there's a question raised last time in terms of why would you? I think it's in the first problem, right? In the first problem, you have aliasing, right? Aliasing. So in other words, when you take the Fourier transform, it's all periodic signal, right? It's when you take a Fourier transform, it's all periodic signal. We just look at this in time and in frequency domain. However, when you have this curve, right? If you have a pulse, right? So for example, I have a pulse very narrow pulse, right? If I have a very narrow pulse, in this case, I need to increase the t, total t, right? But if you have a very narrow pulse and you have the specific number of n, so delta t is capital T divided by n, right? So if you have a very narrow pulse, then you don't have enough resolution. You don't have enough resolution. Your pulse looks like this, right? So you want to, because that's how you sample the pulse, right? That's how you sample the pulse. In order to have a smaller delta t to have better picture, you need to decrease the t, right? Total time span. Alternatively, you can increase the total number n to twice, right? To twice. So either way is fine, but it's actually interesting, right? Interesting. So you have the whole discretization. Sometimes you need to increase the t. Sometimes you need to decrease the t, just depending on what you need, right? So what you need to do is have this, code already, have this sample code. So adjust it so you could, better understand the system, right? Better understand the system. Okay. Any questions? Kind of quick summary on what we did previously. Okay, so now today we're going to cover new material. So dispersion is a linear effect. So today we're going to study nonlinear effect. So the nonlinear effect. So that those two are the major, major effect in the optics. So when the light propagating, they play an important role together in terms of dispersion and nonlinearity. Right? Okay. Okay, great. Let me turn off my cell phone. Okay. This is the nonlinear effect. Right? Let's see. Okay, great. Hopefully you all still can see. It's nonlinear effect. Nonlinear effect comes from the change of refraction index in propagation to the intensity. So it is due to the change of refraction index. Refractive index. Let me leave half over there. In propagation to the intensity, right? So this delta n is n2 times intensity. So if I have power, right? If I have power, so it will change accordingly depending on the intensity, right? It's the intensity. It's the intensity. Okay. So this index change. Due to the change of the index, we can write down the equation I partial u the t partial z plus gamma u z t absolute value square u z t equals 0. We will not talk about what is this equation, how this equation coming from. So this is I don't want to get into too much detail, but instead we will study how to solve this equation, right? How to solve this equation. So this is the nonlinear equation, right? Nonlinear equation. What is the u? U is still the pulse, right? U is still our pulse. So u z t plus gamma. Gamma is nonlinear coefficient. U z t absolute value times u z t equal to 0, right? Equal to 0. Okay, let's solve this equation. So I will do the same thing. We will move the UZT to the left-hand side. Not actually left-hand side. Let's actually divide by UZT and then times DZ. Right? It's the similar procedure. Right? So I partial U ZT and UZT. Okay, plus gamma UZT absolute value square. We will have this partial U, right? Partial Z equal to 0. Partial Z equal to 0. So we will assume we're only taking a small steps, right? We're only taking small steps. DZ is small. So this UZT doesn't change a lot. So there is an assumption that DZ is small. We don't change this. We take into we assume this is a constant, right? Within a small DZ. So let's integrate, right? Integrate, that's what we have. It's the integration of du over u is the natural log, right? So it's nature log u z t from 0 to L plus gamma absolute value u 0 t, right? Absolute value z 0 to L equals 0. So here I will use this 0. So assume does not change a lot, right? So assume this does not change a lot. But however, for each steps, right? For each steps, so you just take a small step. So you propagate from this step to the next and then next. So this value should be the beginning starting point, right? Beginning starting point. So that's the beginning starting point. Okay. Okay, now we're able to solve this this equation. Let's move this piece second term to the right hand side. Right, the whole nature log, right? Nature log u propagating LT over u 0t equals I gamma u 0t square L, right? Nature log ULT U0t equals I gamma U0t square L, right? Okay, so we move this piece second term to the right hand side, move this I to the right hand side, the negative cancel out. So this is the nature log, right? I mean, please feel free to interrupt me if you this integrate I, you cannot see I, but this is integrate. Any question, please let me know, right? Feel free to interrupt me. Okay, so then we can move this L, right? So we can move this multiply, have exponential in the bottom, exponential here, exponential there, and then we can have ULT equals U0t, right? ULT equals U0t and multiply by exponential, right? So it's exponential I gamma U0t absolute values L. Okay. So we'll just take an exponential, multiply U0t. Exponential, then we multiply U0t. Okay. Okay. So now let's look at this, right? So if we take an absolute value, let's see, if we take an absolute value, what happened, right? So ULT and U0t. We take absolute value square, absolute value square. Can you tell me, is that what's the relationship between this ULT and U0t? So is that should be, which one is bigger or smaller? Any relationship between ULT and U0t? Any thoughts? So you like the left hand side is going to be bigger. The left one is going to be bigger, or the right one is bigger, or they're equal. Any thoughts?
Wouldn't
Okay.
the right one
Go
be
ahead.
bigger?
Go ahead. Can you speak loud?
Wouldn't the right one be bigger?
the right one will be bigger. Okay, so any other thoughts? Okay, so how much is the exponential I pi absolute value square? Okay, so let's do it, right? So exponential I theta, right? So what is exponential I theta? So this is cosine theta plus I sine theta, right? So anyone can tell me what's the exponential I theta square absolute value square? How much is the exponential I theta absolute value square?
It's going to be 1.
That will be 1, right? Okay, so it is actually cosine theta square plus sine theta square, right? Because you need to take the absolute value and square. So this is cosine theta square plus sine theta square equal to 1, right? So then this will be, if we take absolute value on the both left and right hand side, then I need to time this exponential, whatever, all this big chunk absolute value square. Can you all see it? Yeah, okay, great. So, but this term turns out to be equal to 1, right? This term turns out to be 1, and in the end, what we have is those two terms are equal, right? Those two terms are equal, but that's okay. This is for discussion. I'm glad, let's participate and let's learn together, right? That's okay. So they are the same. They're the same. Okay, what does it tell us? From this equation, what does it tell us? So if I have a path, right? If I have a path and in time domain, right? So this is z equal to 0, z equal to L, and they are the same path shape. The amplitude is the same. The phase is different, right? The phase is different. What is the phase difference? The phase difference is is by this piece, right? This is our theta. If we propagate long, then it will change with a big difference in phase, right? But if we propagate small, L is small, there's small difference, right? But let's recall what we learned from the dispersion. Dispersion, you have omega, right? So you have omega. So this is z equal to 0, z equal to L. Are they actually, we learn, will you be able to plot the pulse? If we have this in frequency, we're only looking at the dispersion. The pulse, the amplitude is the same, right? The phase is different. The phase is different. Phase is different, right? In frequency domain, the dispersion does not change the amplitude. So for the nonlinear effect, in time domain, it does not change the shape, but the phase is different, right? Right. No change in shape, right? No change in shape. the pulse shape, it doesn't in time domain. In time, right? Here, dispersion, no change in shape in frequency domain. In frequency domain, right? In domain. So that's actually a very important concept, right? What is dispersion? What is the nonlinearity? Let me move this mouse away. Yeah. Okay. So in dispersion, as we learn, that's the equation is u z omega tilde equal to u 0 omega tilde exponential I over 2 k naught double prime omega square z, right? Delta z, whatever. So this piece is what we did on the frequency domain. If we take absolute value square, this exponential I theta is 1, right? Exponential I theta is 1. So it does not change the frequency domain. But here's the nonlinear equation. Nonlinear equation, if we take absolute value square, the shape, pulse shape or pulse amplitude doesn't change, no change in shape, but the concentration, but the phase is different, right? But the phase is different. Yeah. So it's actually kind of like two opposite beasts, right? So one is actually make change in dispersion, change in the frequency domain, but it doesn't actually add the phase in the frequency domain. Of course, in time domain, it will change the shape, right? So here we add the phase in time domain, no change in the shape, but it will change the shape in frequency domain. Okay, so that's the basic characteristic for the nonlinear effect and dispersion effect, right? Any questions? Okay, so let me write the, do I have the, right? Yeah, okay. So in this case, let me summarize. This is the same, let me use a different pen, right? Okay, so same, oops. So it will be the same pulse shape. Can you all see it? Yes. Same pulse shape in time domain. Time domain, right? Change in spectrum, right? Change in spectrum. Okay. So that's this. That's what we did, right? That's what we did. Okay. So now. Now, let's do this nonlinear effect. What is gamma, right? So it's nonlinear parameter. Nonlinear parameter is gamma. Gamma is omega naught n2 over C effective area. Right? So this gamma. So omega naught is the frequency, right? Is the angular frequency, right? It's the omega naught is the angular frequency, which is 2 pi omega, omega is 2 pi f, right? Omega 2 pi f, f is frequency. C is the speed of light. And then N2 is the nonlinear parameter, the Kerr parameter. So it's actually N2 is there's a special name. It's called Kerr parameter, right? So remember this delta n, right? Delta n is n2 times intensity, right? So this parameter meaning that whatever intensity change will be reflected on the index change, right? Index change. Okay, this A effective. So A effective is effective area. So meaning that what is the pulse, area? So effectively, what is the pulse area? The laser beam, right? What's the laser beam area? Okay, let's look at the silica. So silica roughly 2.6 times 10 to the negative 20 meter square. So it's the watt, right? So in other words, intensity is watt per meter square. So my silica, this N2, right? So this N2 equals this number, right? So it is totally the object unit with respect to this intensity. So delta n is unitless, right? Delta n is unitless. It is the index, right? 1.5, 1.4, 1.6 ish. So let's look at the unit for gamma. Let's look at this. So frequency is 1/second, right? 1/second. And then N2 is meter square over watt. And then C, speed of light, is meter/second. Effective area is meter square. I'm just looking at the unit, right? Not talking about the value, but the unit. Okay, so all together is meter cancel out, second cancel out. It is the 1/meter and 1/watt. Right? So let's usually write as meter inverse, watt inverse. Right? Meter inverse, watt inverse. Okay. Okay. Now let's look at the equation again. Right? Let's look at our equation again. This is the nonlinear Schrodinger equation. It's called, that's very generally used in the, photonics, right? It's called nonlinear Schrodinger equation. So it's nonlinear Schrodinger equation. Can you all see it? Yeah, okay, great. Nonlinear Schrodinger equation. So there's the called NLS, right? Abbreviation is NLS, nonlinear Schrodinger equation. Okay, so the equation looks like I du dz, right? dz equals negative I, right? Let's use partial, sorry. Let's use partial, right? Partial u, partial z, right? Partial u, partial z equals negative I alpha over 2u. And then plus k naught double prime, that's our old friend, k naught double prime, right? Divide by 2, remember this divide by 2, partial u square, partial t square, second derivative, right? Second derivative, and then minus gamma, absolute value u square u. So now we're familiar with I du dz is k naught double prime over 2, partial u, partial t, right? Partial u, partial t. And this is the loss term. This is the loss. So this is the loss. This term is dispersion. Right? This term is nonlinear. Nonlinear term. Right? Dispersion, loss, dispersion, nonlinear term. Right? So we have learned this dispersion. Used quite several weeks, right? So through the lab, I think you understand. It helps you to understand, hopefully. And then today and in the next class, we'll focus on this nonlinear effect. We'll focus on nonlinear effect. But that's how you are going to learn altogether, right? So we will learn dispersion and nonlinear effect, right? Okay, so next, let's simplify this equation, right? Let's simplify this equation. Let's assume, let's replace normalized amplitude. We have the normalized amplitude, right? So this would be U ZT equals square root of P exponential negative alpha Z over 2. Can you all see it? Oh, you're almost on the boundary. So let me write as here.
Dr. Who, sorry, what is under the square root sign there?
This is P, power. So this is P.
Okay, thanks.
Yeah, thank you. Thanks for interrupting me, right? It actually makes me feel better. There's people listen to me, so it's good. So please feel free to interrupt me and ask questions. So it's the power. So now we normalize it, right? Again, so in other words, my A will be 1, right? A will be 1 because I take a square, it will be power, right? It will be power. So A will be normalized, right? In the same time, we actually add this exponential negative alpha Z over 2. But what is this? I mean, you will tell it's actually a loss term, right? If you increase the Z, it will exponential decay. It will exponential decay. So this is the loss term. This is the loss term. The purpose of adding this term, later on you will tell that we actually cancel out this loss term. So we're able to add a normalized format. Then let's solve for A. Once we have A, we go back into this equation. We should be able to identify U, right? We should be able to identify this U. So that's the main idea, right? Main idea is to have this A and then have this A, then come back and identify the U. Okay. Okay. So let's do the substitution, right? Let's substitute this into the original equation. So let's do it together. So first one will be partial U, partial Z, right? Partial U, partial Z. We have 2Z here, right? So in other words, it's the UV derivative. It's U derivative V plus UV derivative, right? So it's the it's the derivative. So let's first take the derivative on this U. So this is the I square root of P, right? I square root of P. Take a derivative on exponential negative alpha Z. So it's have negative alpha over 2. And then exponential negative alpha Z over 2, right? AZT. AZT. Right? So that's the first derivative on the first piece, exponential. Then now we have derivative on A. So it's plus square root of P exponential negative alpha Z over 2 and partial A partial Z. right? ZT. Okay, that's good. Oh, I missed an I. There's an I term. So there is an I here. So it's I. Okay, so this is the left-hand side. Right-hand side will just simply negative I alpha over 2 times U. What is U? Square root of P exponential negative alpha Z over 2 A ZT. Right? Okay, so that's this term, the first term, right? The last term. Okay, then we add the dispersion, right? We add the dispersion, it's with respect to t, right? So we normalize the amplitude, we take a partial derivative with respect to t, second derivative. The t only contained in the a, so we'll just transfer this derivative to this a, right? So let's take a derivative. So it's k naught double prime over 2, and then square root of p, right? Exponential negative alpha z over 2, and then take a derivative with respect to t twice, right? So in other words, we take a derivative on UZT, a second derivative. So, but the only parameter contained t is the a, so we'll just take a derivative on this a twice, right? Second derivative. Okay. Now we'll do the last term, right? So last term is the gamma, the absolute value u square u, right? Absolute value u square u. So in this term, let's have gamma. It's a negative gamma. You can see it. So absolute value square, right? Absolute value square p, right? And then absolute value square, it is square exponential negative alpha z, right? Because it's square, right? Absolute value square. So the 2 is canceled out. And then we need to take absolute value square a. I'm going to make an abbreviation, right? So ZT, skip the ZT, otherwise, let me write the ZT here to be consistent, right? ZT, absolute value. Can you see it? Barely, but I think we will survive. Okay, that's it. And then we follow by the square root of p exponential alpha z over 2 negative. And then we have AZT. Yeah, that's it. Oh, we barely make it, right? Okay, that's all. Any questions in terms of this equation? Okay, so now let's actually simplify this equation, right? Let's simplify this equation. It's the, we'll see that it turns out that on the both left-hand side, this term and the right-hand side first term, they are the same, right? They're the same. So they all have negative square root of p I alpha over 2 exponential negative I alpha z over 2 AZT. So these two can be canceled out, right? These two can be canceled out. Okay. At the same time, we also want to change the tau, right? We want to normalize the t. So we make the plot on t as t0, right? We plot t over t naught. So why don't we actually have a new tau? Why don't we have actually a new tau? Let's use a new tau. And we also look at this. On both terms, it has square root of p exponential net. All the terms has square root of p exponential negative alpha z over 2. Let's remove this term, right? So let's use the replace the tau and remove square root of p exponential negative alpha z over 2. Remove all these terms. So let's use the substitute tau, right? So now, for example, let me write it, right? So this exponential, this is gone, this is gone, this is gone. Right? So they were left with I partial A partial Z dt equals this k naught double prime, right? Equals k naught double prime over 2 partial A Z t, but now we make it into a tau, right? We make it into a tau, and then this t, right? So what is t? T is tau times t naught, right? So we have partial tau square, take a second derivative, so it will be tau times t naught. Let's write this t naught here, square, right? And then minus gamma p, and then exponential negative alpha z a. This time I don't have space. Let me write, a simplified version, right? But this a is actually z tau, right? So let me be correct. This will be tau 2, right? This will be tau 2. Okay. Any questions on this equation? Okay. Now let's look at it. So this equation become I partial A. Let me just write a simplified version, right? So then let's do this k naught double prime over t naught square. Can anyone tell me what is the k naught double prime over t naught square?
Is that the dispersion length?
That's the dispersion length. It's actually inverse dispersion length, right? Remember, LD is t naught square over t naught square over k naught double prime. Yeah, that's the dispersion length. No, it's the absolute value of this, right? Because k naught double prime could be positive, could be negative, right? They all actually play a role for the broadening, right? So now let's do this. It's the dispersion length. It's 2LD dispersion length, but we need a sign for k naught double prime, right? If it's positive, negative, right? So SGN, that's the representing the sign, right? So if the k naught double prime is negative 123, this SGN sign is negative 1. If the k naught double prime is positive 0.01, then this SGN is positive 1, right? It's just the sign. It's just the sign over 2LD, and then partial A, partial tau, second derivative, right? Second derivative, and minus exponential negative alpha z divided by, now let's introduce a new term called LNL. This is 1 over gamma p. 1 over gamma p. So this is the nonlinear length. This is nonlinear length. So A absolute value absolute value square times A.
Dr. Who?
Yes.
Just to make sure I got that right, the gamma p term turns into the nonlinear length.
Yes, that's the nonlinear length. Yes, you're right. It's 1 over gamma p. Yeah. So in other words, you think about nonlinear length, right? This is dispersion length. We are the expert by now, right? The dispersion length. So nonlinear length. So if we have more power, we should have smaller nonlinear length, right? So that means the nonlinear effect is stronger, right? So we have more power. That means nonlinear length is small. That means we have strong nonlinear effect, right? So in other words, we have a small nonlinear length as once my fiber or my optical device has a length comparable to the nonlinear length, then we'll have nonlinear effect, right? It's the same thing as the dispersion length. So I know it's kind of tricky at the beginning, right? So once we have high power, the nonlinear length is going to be small. Once we have small nonlinear length, that means we have strong nonlinear effect. Okay, so now we have different scenario, right? So I'm going to have different scenario that in the case L much less than nonlinear length, L much less than L dispersion, right? So how would the dispersion, if the L is way less than nonlinear length, L is way less than dispersion, how would dispersion and nonlinearity play a role here? It will neither of them will play an important role, right? So it's neither dispersive nor nonlinear effect. Neither nonlinear effect play a significant role, right? So if my L is way less than LD, L is way less than L nonlinear length, L is way less than LD, it plays almost no role, right? Why? Because you think about this dz, right? So if my dz is way less than d tau, right, and way less than L and L, so all this contribution on the right-hand side all be zero. So dA is no change. dA has no change, right? And we also actually plot on this in the homework, right? Remember, in the homework, we have this pulse, and then we have this and that, right? So this is LD, 2LD, this is the 4LD, right? So it needs to be at that dispersion length in order to play an important role. It needs to be at the dispersion length in order to play an important role, right? So if we have almost 0.1 LD, almost no change. Almost no change. Okay, so let's have an example, right? So quite calculation here. So we need to actually make sure we understand. So let's assume that for the case L is about 50 kilometer, right? L is 50 kilometer. We need LD and L nonlinear length will be larger than 500 kilometer, right? It's the 10 times in order change. So in here, it's the effect, it should be 10 times. So the pulse change is relatively small, right? For dispersion-free transmission. Dispersion and nonlinearity free, right? And nonlinear effect, nonlinear effect free transmission. Right? But when I say dispersion of nonlinear free transmission, you would say, aha, you know, this is you still have 0.1%, you still have 10%, right? Still have 10% effect of 10. But usually in the optical transmission, there are all other effects. As long as it's not the dominating fact, that's okay. All right, so let's look at it at lambda equal to 1.55 micrometer, and the K naught double prime. K naught double prime is absolute value of the K naught double prime is 20 picosecond over a kilometer, right? So gamma is 2 inverse watt inverse kilometer, right? Remember, we have inverse watt and inverse meter, but in this case, it is the kilometer, right? We just write down the kilometer to make this number, you know, simple. Okay, so with that, so this is the wavelength fiber property, right? What we can change is the T naught and the P, right? That's the pulse. So find T naught and the P naught. Find T naught and P naught when LD equals L nonlinear length 500 kilometer, right? 500 kilometer. Okay. Hopefully you have the pencil or piece of paper, or let's do a small exercise, and find the T naught and the P naught. So if you find it, just let me know. So just use piece of paper and find the equation here. I think we have all the equations on the board. So I want to have the dispersion length and nonlinear length as 500 kilometer. This is my lambda, K naught double prime, gamma, right? And we'll find the T naught. How much is the T naught? How much is the P naught? Any numbers?
Would T naught be 100 picoseconds?
That's good. P naught is 100 picosecond. How about P naught?
1 milliwatt?
1 milliwatt. Yeah, that's good. Okay, so what is T naught? T naught is this equation, right? So square root of LD times K naught double prime, but let's do absolute value, right? So what it is, LD is 500 kilometer, 500 kilometer times K naught double prime. What is the K naught double prime? Is this, right? So let me have some space times the 20 picosecond square over kilometer and take a square root. This happened to be 100 picosecond. Okay, can you all see it? Yeah. Okay. Yeah. Okay. Then we have P naught. Yeah, I have a lot of space here anyway. So we have P naught. What is the P naught? P naught is this, right? Nonlinear length. So it's the 1 over nonlinear length times gamma. This will be 1 over 500 kilometer times gamma. What is gamma? It's 2 inverse watt inverse kilometer. And this is the, you will find out 1 milliwatt. Right? Okay, so think about it, right? So this T naught determines the LD. T naught determines the LD. So if you have wide, if you have wide T naught, right? That means very wide T naught, dispersion length going to be large. Dispersion length going to be large. Why? It's because if you have a very wide time domain pulse, the spectral domain going to be small. So it suffers less in the dispersion effect. That's why LD is wider, right? So this T naught directly controls the LD. Now this P directly controls the nonlinear effect, right? Why? Because once we have high power or high intensity, we're going to change the refractive index a lot. So once we have high power, going to be small nonlinearity, small nonlinear length, but strong nonlinear effect. So P is determined by 1 milliwatt. So this T and the P will play an important role in determining nonlinear length and dispersion length, right? And we will actually, that's the material today. We will elaborate more of this, comparison between nonlinear effect and dispersion effect in the next class. Any questions? And homework is due this Friday. Yeah, I'll make the end of Friday. So I think almost you all did it, finish at least the figure, right? Yeah. Any questions? Okay. Okay. So that's all, and I'll see you this Friday, right? Because we don't have the Monday's class. I'll see you this Friday. Okay, in 2 days. It will be all online. Yeah.
Right, thanks,
Okay.
Dr. Yu.
Thank you. Bye.